Hello, everyone. This is the lecture for section 1.1 to 1.2 for Math 210S, functions notation, domain, and range. Okay, so we are starting from scratch for learning calculus. Okay, so there's a bunch of stuff that we need to cover beforehand, right? In particular, for this section, we're going to be covering how we represent functions, how we represent stuff in the mathematical world. Okay, that is our functions notation. Okay, and because of how we write functions, right, there might be certain things that we can't do with our functions. Okay, and that is going to be me covering domain and ranges for functions. Okay, so that's what's coming up in this section. So let me go ahead and start getting into the sort of the nitty gritty of all this stuff, right? So the first thing I'm going to define is what the heck a function is, okay? A function, okay, is a relationship. It's a relation between two sets of values, okay? Each possible input value leads to exactly one output value. If you have something that does that, we call that relationship a function, okay? The language that we use is that the output is a function of its input, okay? As in, think of it as a machine, right? There's a function, you give it something, and it's going to spit something out to you. Does that make sense? That is the definition of a function, okay? The set of input values, we call that something specific. We call it a domain, okay? And the output values from those input values, we call that the range. Okay? Okay, so I've got a couple of examples here to spell out what is and is not a function. Okay? So the first one, let's go ahead and start with A. Okay? If you take a look at this relationship, right, we have inputs P, Q, R, and the outputs are M and N, right? If you take a look at this exact definition that's right here, I'm going to highlight it in blue, right? If you take a look at that, every possible input goes to exactly one output. This does it. A does it. Got it? Okay. Same thing with B. B also, every input goes to exactly one output. Okay. C, this is not a function. So there's a problem here. That means, right, that rule in blue gets violated somehow, okay? And the way it gets violated is by this one right here, okay? We have a function value, we have a value of in the inputs, Q, that goes to two outputs. We can't have that, not a function. Okay, whenever something like that happens, we have not a function. Okay, so pictorially, I think this makes sense. Okay, now what I want to do is let me scroll down a little bit and get into functions notation in particular. Okay, functions notation, this is how we really write our math out. We use this notation right here, right? That the y value is equal to some f of x value, right? Okay, the way that we read it is this right here, that y is a function of f of x. Okay, the x variable represents values, input values, okay? And we call those the independent variables, and the y values, which we know are equal to f of x values, right? They are the output values. The other word we call them is the dependent variable, okay? As in the y values depend on whatever the x value is, right? Okay? So what I want to do is I'm going to collapse a bunch of theory here, okay? I'm going to show you guys how the function notation works out, at least numerically, okay? And what this is going to produce is going to be a set of x and y coordinates that can go on a graph and we can then have a graphical representation of our function. Okay? So for this example, right, I'm going to be using this function right here, okay? So in order to use it, I need to sort of define some x values, and I've got some set aside already. There's going to be a -2, -1, 0, 1, 2, okay? So how we use this is like this. We would say f of -2. Whenever we write this out, we want to basically, wherever there's an x, we change it to whatever x value we chose. So this is going to be -2 over -2 squared minus 1. Notice that the x's turned into my -2's. Okay, we simplified this out a little bit. -2 over 4 minus 1 is equal to -2 over 3. Okay, this produces, right, what we call a coordinate, an x, y coordinate, or an ordered pair. Okay, the x value that we chose was -2. The y value that we got is -2/3. There we go. Okay, let's do it again, but we'll do it for -1. So now we have f of -1, -1 quantity squared minus 1, -1 divided by 1 minus 1, -1 over 0. Whenever you have something like this, we call this something special. We call it DNE. And what DNE stands for is does not exist. Now keep this in mind really quick, okay? I'm going to come back to it, okay? But I will leave you with this, that whenever you have something that is divided by 0, you can't have it. That is not explainable. We have no explanation for it, so that's why we say it does not exist. Okay? Okay. Let's move on for now. So keep that thought in the back of your mind, okay? Let's go ahead and do f of 0. 0 divided by 0 squared minus 1, 0 divided by 0 minus 1. This is 0. If the 0 was on the bottom, that does not exist. But this one, the 0, let me add actually one more step here. 0 divided by minus 1, this is actually 0. Okay, this is perfectly fine. X value that we chose was 0. The Y value that we got was 0. We're good. Okay, so in the interest of time, if you do f of 1, you're going to get, again, a does not exist. Okay? You're more than welcome to try it out. You'll get the same result. Okay? If you do f of 2, again, in the interest of time, what you're going to get here is 2 over 3. So there's going to be another value here, 2 comma 2 over 3. Okay. So now, what the heck is this, right? What I'm going to do now is I'm going to go ahead and actually let me do purple for this point. There we go. Okay, so for these 3 points, you guys see these? I'm going to graph them. I'm going to plot points on my XY axis, yeah? I'm going to do it in purple. The first one is going to be -2 comma -2 over 3. We have what's called an XY coordinate plane here. So the horizontal is going to be X, and the vertical, the up and down, is what we consider our Y axis. Okay. To graph these, we're going to do -2. So go to -2, and then go to -2/3. So maybe about right there. So this point right here is going to be that first point, -2 comma -2/3. Okay. The next point is 0 comma 0. That point right there. Simple enough, right? The next point is 2 comma 2/3. 1, 2, 2/3, bam, right there. This point is 2, 2/3. Okay. What we're doing here, right, is we're trying to provide a graphical representation, a graph of our function f of x, okay? I only chose 5 points, 5 x values, right? Those 5 x values produced 3 points, the 3 that are on the graph right now, right? If we keep doing this for every single x value, we will get a continuous, a nice connected, smooth looking graph, okay? And that graph is going to look like this, okay? I'm going to go whoosh down that way, and then this goes like this, whoosh, and then it goes like this, whoosh. Oh, sorry, I messed up there. It goes like this, whoosh. There we go. So that blue graph, those blue lines that I actually graphed, right? That is the graphical representation, the graph of my function f of x, okay? Now, I do want to spell out something here, okay, for everybody to see. Hopefully, you guys remember that during the very first meeting for the class, I said that I was going to there's going to be a fair amount of stuff that I'm going to sort of do away with in the interest of everybody's time, okay, to speed through a little bit more so that we can cover more calculus than the more basic arithmetic in this case, okay? So, and the way that I was going to do it is I was going to use Desmos, okay? For all of these problems, for all of the quick checks, for everything you can possibly think of, right? Use Desmos as freely as you want, okay? But I do want to show you at least once, okay? So let me open up Desmos, okay? Let me actually delete it so we know the outcome, okay? So what I'm going to do, and this is why I like Desmos so much, and let me make this, okay, it's already set up, okay. I'm going to do a double screen. I'm going to do this thing, bam and bam. I want to graph that f of x value, right? The reason why I like Desmos so much is because when you type it in, x divided by x squared minus 1, it makes it look like the thing that you were looking for to begin with, right? And if you take a look at my graph, look at that. It's crude, it's god-awful, but I mean, I did pretty good, right? In particular, it matches my graph that's through Desmos. Okay. All right. We're getting somewhere. We're cooking. Okay. So what I want to do now is in class, this is going to be your very first quick check for this class. There's a problem here. Evens will do this one. Odds will do this one. I want you guys to replicate basically what I did, okay, with 2 separate functions, okay, and at least provide me the graph, okay, and we'll come together and we'll share our results after that, okay. Like I said, use Desmos as freely as you want, right? For the purpose of getting yourself out of doing all the menial algebra, all the menial arithmetic, the tedious stuff that is sort of inconsequential to the thing that we really need to learn, which is calculus. Okay? Okay. So now, if you recall, let me go back up here. You recall, there were 2 values that produced does not exist. Okay? These 2 values that produced does not exist, we need to kick them out. Okay? And the reason why is because they give us something that we have no explanation for. Okay? So that's what we're going to do right now. But before we do that, okay, I need to show you guys what's called interval notation. It's essentially a method that mathematicians use to express large collection of numbers. Interval notation, okay, in a simple and compact way. Okay, so let me scroll down a little bit more. Let me cover how interval notation looks like, okay? So I've got 4 columns here, okay? The description, the inequality, what it looks like on the number line, and then the actual word description of it, okay? And what I'm going to do is fill in that second column with what the interval notation would look like, okay? So the first one, suppose that x is greater than a. How do we represent that? We know that it looks like this right here, right? But how do we represent it in an interval notation? The most sort of simple, compact way possible. And the way that we do that is this, a comma infinity. Okay. Suppose we wanted to do values less than a, negative infinity to a. Okay. Suppose we want values greater than or equal to a, right? A infinity. And then let's say you want less than or equal to negative infinity to negative a. Oops, sorry. Negative infinity to a. Okay. Now, I think I need to add some language here. Okay. And I'm going to do it right here up above. Strictly greater than and strictly less than. Okay. Now, I think I need to provide you guys an example with what I mean by strictly greater than and greater than or equal to. Okay. And the way that I'm going to do that is I'm going to scooch this over really quick. I'm going to give you guys 2 sets here. Okay. I'm going to do it on the right here. So suppose I had this, right? 3, comma, infinity. And suppose I had this, 3, comma, infinity. Notice that the top one has round brackets or round parentheses, right? But this one has the actual hard bracket, the hard square bracket, right? So what's the difference between these two? Okay. In the first one, in this one, okay, it is all numbers strictly greater than 3. Okay. So for example, 7 is in there, 6 is in there, 5 is in there, 4 is in there, 3.5 is in there, 3.1 is in there, 3.00000001 is in there, right? But the value 3 is not. Got it? Okay. The only difference between this set and this one down here is that the bottom one does include 3. So you can say that that top one, right, with the both the round parentheses, is inside the bottom one, right? And the bottom one just sort of includes that missing value. It includes the endpoint. Got it? Okay, we'll get some more practice in as the semester rolls along, okay? Okay, at this point, right, I want you guys to take a look at this. Round brackets means you don't include. The square brackets means you do include. Got it? So we get to move on with basically that explanation you could take to the bank, right? So let's say I wanted to describe everything between A and B, but not including A and not including B, right? That is equivalent to saying A, comma, B. Okay, suppose I wanted to include the lower value, A. So A to B, that's still the same, right? But I don't want to include B, but I do want to include A. Done. Okay, suppose I want to do B, but not A. So Notation is still the same, A, B, but I want to include B, but not A. Done. And then let's say I wanted to include both ends. A, B, bam, bam. Okay. So if I want to include the value, I use the square brackets. If I don't, I use the round ones. All right. There is something I need to point out that is really going to be required, not only for what's coming up in the next section right now, but throughout the semester, okay? And that is the diamond method. Some of you guys might remember from high school something called the diamond method. It's unfoiling a multiplication, okay? So suppose we had something that looks like this. I know I'm running a little fast here, right? Suppose we had something that looks like this, a function that looks like x squared plus bx plus c, okay? And we want to factor this. We want to do something like this, that we want this equal to something times something, okay? It's going to be an x plus blah, 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 something, right? And then an x plus another blah, 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 right? Okay, how do we break this back up so that we get this back? Okay, and that, if you guys recall from high school, was called our diamond method, or unfoiling. Okay, so as just a procedure, let's go ahead and do this. Suppose we had this, right? What is the unfoiling? What do we have to multiply together in order to get this back? Okay, and this is where we employed what's called the diamond method. Okay, now there's different names for it. Some people call it the box method. Some people call it the diamond. Whatever you remember from high school, go ahead and use it. Okay, but I'm going to cover it. And I'm going to call it the diamond method in class. Okay, so suppose you had something like this, the x squared plus 2x minus 35, right? Give me two numbers that add the 2 and multiply to negative 35. Okay? Give it a thought. Okay? The two numbers are 7 and negative 5. Okay? So that means that my f of x, which is equal to x squared plus 2x minus 35, is also equal to x plus 7, x minus 5. Got it? Whoa. I don't know what happened there. There we go. Okay. Just to double check, what I'm going to do now is I'm going to foil everything. So if you guys remember foil, let me do it up here. Let me do it in capital letters, huh? And let this thing actually erase. Come on. What's going on? Yeah. F-O-I-L. That stood for first, outer, inner, last. Okay, this is how we had to group these. So this times this would be our first. Okay, this times this would have to be our second, or our outers, right? This times this would have to be our inners. Let me make that a little thinner. And then this times this would be our lasts. Okay, so just to double check, right? Our first is be x times x. That's going to be x squared plus x times negative 5. That's going to be minus 5x. 7 times x plus 7x. And then 7 times negative 5. That's going to be my negative 35. And if you combine the like terms, these two in the middle, x squared plus 2x's now, right? minus 35. So turns out, right, if you take a look at this, this is equal to the thing that we started with. Yay! Okay, so this is how you unfoil this multiplication. Okay, and this is how you would double check it. Okay, I've got a couple of examples there. I want you all to try it. I'll sort of guide you guys through the class, help you guys out through the class. But I do want everybody to pick up this. We are going to be using it repeatedly in our next couple sections. Okay? Okay, we're getting closer. I know this looks like a collection of stuff that is sort of unrelated, but believe me, it's related. Okay? Let me go back to a set of definitions that I covered in the beginning, right? The domain, right, is all possible input values, okay? And all possible output values from those domains is called the range, okay? I know those are sort of wordy definitions, right? The better idea is to use sort of like a pictorial definition, okay? Or a visual representation. Over here, you have x values, okay? The collection of x values is the domain, okay? And over here, you have the range. These are y values, right? But not all y values. It is all the y values that are associated to an x value in the domain. So we're hitting this with a function f, right? And this is why we say that this y value right here is f of x values. This is the sort of the visual representation of domain and range. Okay, I think we've got enough to start doing domains and ranges of functions, okay? So as we saw in our example, okay, there are certain values we can't plug in because they produce things that we have no explanation to, okay? The two big ones that we have to watch out for are these. The first one, we cannot divide by zero. So something divided by zero is just does not exist. We have no explanation for it. So we say does not exist. We write it out. Okay. The second one is that one. We cannot have the even root of a negative number. So the square root of -5, the fourth root of -12. Okay. All of those are not possible. Okay. For both of these, we write out D&E. Whenever something like this happens, we just write it out. It does not exist. And we can stop our progress. Okay? So now, how do we figure out the domain of functions? Okay? Procedurally, right, what we do is we find the things, we find the x values that do one of these two things. Okay? We find the x values that do one of these two things. We kick those out. Everything else is fair game. Everything else is fair game. Okay? So, let's go back to my example, right? Bam. There were two. F of 1 and f of -1, both of those produced a D&E, right? Okay? Anywhere where you get a D&E, right? Those are the two values that you kick out. Okay? But how do we figure that out without having to graph it, right? That's where our, there we go. That is where we get our, we're going to use our unfoiling process, right, to find out, okay? So Does it look like we're going to be taking a square root anywhere? No. So the second one is not one that we have to watch out for. So this one's not the one that we need to really worry about. The first one is, since there is a division, right, we have to make sure that we don't divide by 0. So that is our game plan here, right? So bottom, come on, equal to 0. We can't have that bottom equal to 0. The bottom of our fraction, we can't have that equal to 0. So what we're going to do is we're going to find out what makes it 0. I know this sounds weird, right? We're going to find out what makes it 0. Those are the values we can't have. We throw those out. Everything else is fair game. Okay? And in order to solve this out, this is where we need our diamond method. Plus times. Okay, I'm going to rewrite this really quick. Okay? We need two numbers that add to 0 and multiply to -1. The two numbers are 1 and -1. So then that means that this thing right here can also be written as x plus 1, x minus 1 equal 0. Okay, this is getting us closer. Okay? Now, what I want everybody to look at is this. We have something times something equals 0. So we have this going on. We have an A, I need to tone down that thickness right there. There we go. A times B is equal to 0. We have an A times a B, right, equal to 0. What can you tell me about one of these two numbers? One of these numbers has to be 0, right? But we're going to go ahead and take both of the conditions. So either A is equal to 0 or B is equal to 0. This is the only way we can get a multiplication to equal 0, right? If it's not 0, it can be whatever it wants. But in order for us to do a multiplication and have it equal to 0, one of the two values, A or B, has to be equal to 0. So we use that here. Either x plus 1 is equal to 0 or x minus 1 is equal to 0. Okay? From these two, we get these two values right here. Okay, so let's collect what we just found. Okay, we want to find all the possible values for this function right here. All the possible values that we can plug into x. Okay, okay. Since this thing has a division, we can't have the bottom equal to 0. So we're finding what makes it 0, right? And we did. We found what makes it 0. We did this by diamond method, and we got these two values, 1 and 2. These are the two numbers we cannot plug into our function f of x. So we have to kick these out. Everything else is fair game. Okay? So now we need to write this. Now we're getting down to our solution. Okay? So if I want to write my domain, okay, I want to kick out -1 and +1. Everything else is legit. Got it? So in order to do that, my answer is going to be this. For the domain, for my f of x, my f function, right? It's going to be -infinity to -1, union -1 to 1, union 1 to infinity. Whoa. This is my final answer. So notice what's included in here and what's not included, right? Because of how we use our brackets, because of how we're using our parentheses, right? -1 is missing and +1 is missing. Everything else is in here. So this domain, this green thing right here, these are all the possible x values that I can plug in to f of x. Okay? Now, I want to bring up one thing. Remember that thing that I told you to keep in the back of your mind from our example? Okay? Let's go back to our example. Okay. Here is x equal, here's x equal -1. And here's x equal +1. You guys see what's happening there is that it does sort of like this, sort of like split, right? One end goes up, the other end goes down, or vice versa. One end goes down, the other end goes up, right? This is indicative of values that do not exist. Whenever you have a DNE somewhere, right? This is what tends to happen on the graph, okay? So you can find the domain of your function using the graph as well. Okay, so in this case, we saw that -1 and +1 is doing something funky, right? Turns out that's where we have our DNEs, and turns out as we scroll down back to our example in the work, those are the two values we should have kicked out to begin with. Okay, so like I said, right, you can go ahead and use Desmos for these examples. They're exactly the same examples that you were doing before, okay? So give yourself some time. Use Desmos as much as you need to, okay? We'll do these in class and cover the answers together after a couple minutes, okay? I believe that is it. After that is lecture questions. If you have any questions on the stuff that I just covered, please ask during our class time. Come downstairs to my office hours and ask me then, or just plainly send me an email and we'll figure out something from there. Okay? Besides that, happy studying.